1,755 kilometers per second. That's the velocity. That's how fast S5 HVS1 is moving through our galaxy. Not miles per hour, though that conversion is equally staggering. Nearly 4 million miles per hour if you need terrestrial speeds to make the number feel real. But kilometers per second captures the scale better, captures the impossibility better, because at that velocity, this object could travel from Earth to the Moon in less than 4 minutes, could cover the distance to Mars at closest approach, the journey that takes our fastest spacecraft 6 months, in 8.7 hours, is moving at 6% of the speed of light. 6%, not a fraction of a percent, not speeds we associate with asteroids or comets or any natural object we've encountered. But relativistic velocity approaching what we consider the realm of science fiction, rather than observational astronomy. Please like and subscribe for sleepy explanation. Now the truly disturbing part, the detail that makes this more than just interesting anomaly in velocity measurements, is that this speed isn't just fast enough to escape the gravitational pull of any star in the galaxy, no matter how massive, isn't just achieving escape velocity from local stellar environment, is fast enough to escape the galaxy itself. Is velocity sufficient to overcome the combined gravitational attraction of 200 billion stars, all the dark matter holding the Milky Way together, all the mass concentrated in the galactic center? Is speed that means this object, this star, because yes, we're talking about an entire star, not just some chunk of rock, is leaving, is on trajectory that will eventually take it out of our galaxy entirely and into the void between galaxies where it will drift for millions or billions of years before potentially encountering another galaxy if trajectory happens to align. We're not discussing interstellar travel anymore, not talking about objects moving between star systems within our galaxy. We're talking about intergalactic objects, about stars travelling between galaxies, about phenomena that shouldn't be possible through any natural process we understand yet, that observations confirm are definitely happening. And S5 HVS1 isn't alone, isn't singular example that might be explicable through some extreme but rare natural event, is one of dozens we've detected, is representative of population of hypervelocity stars that are blazing through our galaxy at speeds that physics says shouldn't occur naturally yet that telescopes confirm are absolutely real. Before we go deeper, before we examine how 1,000 km/s stars are even possible, and what explanations might account for them, and why the natural framework is failing spectacularly when confronted with what we're actually observing, you need to subscribe to this channel right now. Because what we're documenting here isn't just interesting astrophysics, isn't just unusual stellar population that challenges our understanding. This is potential evidence of engineering on scales we can barely conceive. This is observation that might indicate intelligence operating at civilization levels far beyond anything humanity has achieved. This is discovery that could answer the question of whether we're alone by demonstrating that others exist who can move entire stars across the galaxy. Hit subscribe, enable notifications. This matters more than you realize. The detection of S5 HVS1 in November 2019 wasn't the first hypervelocity star we'd found, but it was the most dramatic. Was the example that made it impossible to continue treating these objects as curiosities that would eventually be explained through conventional processes once we understood stellar dynamics better. Because the velocity was so extreme. Because the trajectory was so clear. Because the observations were so unambiguous that claiming measurement error or questioning whether we'd properly characterized the object became untenable. This was real. This was star moving at relativistic velocity. This was phenomenon that demanded explanation rather than dismissal. The astronomers who first detected it thought their readings must be wrong. That's the natural response when instruments return values that violate expectations. You check calibration, you verify analysis, you look for systematic errors that might explain the anomalous measurement. Because velocities this high don't occur in normal stellar populations, don't appear in the distribution of stellar motions we've catalogued across millions of stars, are so far outside the normal range that they suggest something fundamental is wrong with either the observation or the understanding that led to expectations being violated. But the readings weren't wrong. Multiple confirmation observations using different instruments and different analysis techniques all returned consistent results. S5 HVS1 really was moving at 1,755 km/s, really was travelling fast enough to escape the galaxy, really represented something that natural stellar dynamics as we understood them couldn't easily produce. And that confirmation, that verification that the impossible measurement was actually accurate is what forced the question. What could possibly accelerate an entire star to this velocity? The answer that mainstream astronomy provides, the natural explanation that's supposed to account for hypervelocity stars, centers on the supermassive black hole at the center of our galaxy. Because Sagittarius A star, the 4 million solar mass monster lurking at the galactic core, creates gravitational environments so intense that it can tear apart binary star systems and fling one member away at enormous velocities while capturing the other into tight orbit or even consuming it entirely. This is called the Hills mechanism after the astronomer who first described it. And the physics is straightforward. It's just gravitational slingshot taken to extreme. Binary star system approaches the supermassive black hole. The tidal forces, the difference in gravitational pull on the near side versus the far side of the system, exceed the mutual gravitational binding between the two stars. The binary tears apart. One star loses orbital energy and falls toward the black hole. The other gains that energy and gets accelerated outward. Conservation of energy and momentum dictates that the ejected star can achieve velocities approaching the orbital velocity at the point where the binary separated. And near supermassive black hole, orbital velocities can be substantial, can reach significant fractions of the speed of light for objects orbiting close enough, so the mechanism works mathematically, can in principle produce velocities like what we observe in hypervelocity stars, can explain how you get 1,000 km/s ejection velocities from stars that started in normal orbits with typical stellar velocities of tens or hundreds of kilometers per second. The energy source is available, the physics is understood, the process has been modelled computationally and produces results consistent with observations. Everything checks out. The natural explanation appears adequate, except it doesn't explain what we're actually seeing, doesn't account for the observed distribution of hypervelocity star origins, doesn't match the pattern of where these objects are coming from and where they're going, doesn't work when you examine the population statistically rather than just explaining individual examples. Because if the Hills mechanism at Sagittarius A star is producing these hypervelocity stars, if ejection from the galactic center is the dominant source, then the vast majority should show trajectories that trace back to the galactic core, should have origins consistent with having been near the supermassive black hole in the relatively recent past, should point back to the center when you backtrack their motions through time, but they don't. Most of them don't originate from the galactic center at all, are coming from completely different regions of the galaxy, are showing trajectories that don't intersect the core when you reverse their motions, are indicating that whatever accelerated them to hypervelocity was something other than close encounter with Sagittarius A star. And that's the paradox. That's what makes the natural explanation inadequate despite being physically sound. It works in principle, but doesn't match the observations in practice. Explains how you could produce hypervelocity stars, but doesn't explain the ones we're actually detecting. The numbers are stark. Of the 21 confirmed hypervelocity stars that have been characterized well enough to determine origins, only 2 come from the galactic center. 2 out of 21, less than 10%. That's not what you'd expect if the supermassive black hole ejection mechanism is the dominant or only source. You'd expect the large majority to originate from the core, would predict that occasional examples might show different origins if multiple mechanisms can produce hypervelocity, but that the core should dominate statistically. Instead, we see the opposite, see that galactic center ejection is minority contributor rather than being primary source. 3 more show origins consistent with the Large Magellanic Cloud direction. The LMC is satellite galaxy of the Milky Way, is smaller system orbiting our galaxy at distance of roughly 160,000 light-years, is visible from southern hemisphere as diffuse patch of light containing perhaps 30 billion stars compared to Milky Way's 200 billion. And apparently it's contributing hypervelocity stars to our galaxy, is ejecting objects that end up travelling through the Milky Way at velocities sufficient to escape our galactic potential entirely. Which would make sense if the LMC contained supermassive black hole that could execute the same Hills mechanism that Sagittarius A star performs. If it had million solar mass or larger black hole at its center, capable of tearing apart binary systems and flinging stars away at extreme velocities. But we've looked for such a black hole in the LMC, have conducted extensive observations searching for the accretion signatures or radio emissions or other indicators that would reveal presence of supermassive black hole, and found nothing. The LMC appears not to have central supermassive black hole, or if it does, the black hole is so quiescent, so inactive, that it's not producing any of the signatures we'd normally use to detect it. And that's problematic for the natural explanation, because if 3 hypervelocity stars appear to originate from LMC direction, if that's statistically significant contribution to the population, then you need mechanism in the LMC capable of producing those velocities. The obvious mechanism is supermassive black hole ejection, but the black hole seems to be absent. So either we're missing something about the LMC, either there's a black hole we haven't detected despite looking carefully, or the apparent LMC origin is misleading and the stars actually originated elsewhere, but their trajectories happen to point back toward LMC coincidentally, or there's different mechanism operating that we haven't identified yet. 5 more hypervelocity stars have ambiguous origins, can't definitively determine where they came from based on trajectory backtracking and stellar age estimates. Might have originated from various locations depending on assumptions about their formation and evolutionary history. Can't be clearly attributed to any specific source region. Just add uncertainty to the picture rather than supporting or refuting particular mechanism. And the remaining 11, the majority of the characterized population, show origins from various regions of the galaxy that have no obvious connection to supermassive black holes or to any other identified source that could plausibly produce the required velocities, are scattered across different locations, are indicating that whatever produces hypervelocity stars is either operating in many places, or is transporting stars to these apparent origin points from elsewhere, or is creating trajectories through some process we don't understand that makes the apparent origins misleading. None of this fits the clean natural explanation. None of this supports the narrative that supermassive black hole ejection accounts for the phenomenon. Instead, we're seeing population that's distributed in ways that natural mechanism struggles to explain. That requires either invoking multiple separate sources using different mechanisms, or accepting that our understanding of how these velocities are achieved is fundamentally incomplete. And that incompleteness, that gap between what theory predicts and what observations show, is exactly where alternative explanations become relevant, where the artificial hypothesis stops being wild speculation and starts being serious consideration. But before examining artificial possibilities, before discussing stellar engines and civilizations that can move stars, we need to understand just how problematic the natural explanation becomes when you look at broader context. When you examine not just the hypervelocity stars in our own galaxy, but the population of intergalactic stars more generally. Because hypervelocity objects aren't just theoretical concern in the Milky Way, they're observable phenomenon across the universe. And what we see when we look at galactic clusters, when we examine populations of galaxies and the stars between them, creates additional constraints that the natural framework has trouble satisfying. Galactic clusters contain dozens to thousands of galaxies bound together by gravity into single large-scale structure. And when we observe these clusters carefully, when we measure the light coming from them and analyze where that light originates, we find something surprising. Roughly 15% of the total starlight is coming from between the galaxies, rather than from within the galaxies themselves. 15%. Substantial fraction. Not tiny contamination from occasional ejected star, but significant population of intergalactic stars that exist in the voids between the galaxies that make up the cluster. And these stars can't have formed where they are, can't have originated in intergalactic space. Because star formation requires dense molecular clouds where gravity can overcome thermal pressure and compress gas to the point where nuclear fusion ignites, and intergalactic space is empty. Has densities far too low for gravitational collapse to occur. Has no mechanism for creating new stars. So the intergalactic stars must have been ejected from their parent galaxies, must have been accelerated to velocities high enough to escape their original gravitational homes and end up drifting in the space between. And if supermassive black hole ejection is the mechanism producing these intergalactic stars, if the Hills mechanism operating at galactic centers is what creates the velocities needed to overcome galactic escape velocity, then we can make predictions about what the intergalactic star population should look like. Should see evolution with time, should find that younger galactic clusters have fewer intergalactic stars because their supermassive black holes have had less time to operate and eject stars. Should find that older clusters have more intergalactic stars because the ejection process has been operating longer and has built up larger population in the intergalactic medium. But that's not what observations show. When you look at galactic clusters of different ages, when you compare young clusters that formed relatively recently to old clusters that have existed for billions of years, the fraction of starlight coming from intergalactic stars remains roughly constant at that 15%. Doesn't show the expected evolution, doesn't increase with cluster age the way the ejection mechanism would predict. Just stays stable regardless of how long the supermassive black holes have been operating, and that constancy is difficult to explain naturally. Because if ejection is a continuous process, if galaxies are constantly losing stars to intergalactic space through black hole interactions or supernova kicks or any other mechanism, then the intergalactic population should grow over time, should accumulate, should show correlation with age where older means more intergalactic stars. The fact that we don't see this correlation, that the 15% remains consistent across different ages, suggests either that the ejection rate is somehow balanced by processes that remove intergalactic stars at exactly matching rate, which requires coincidence, or that the intergalactic population is maintained by different mechanism that doesn't depend on cumulative ejection over galactic history. Neither option is satisfying for natural explanation. Balance between ejection and removal requires fine-tuning, requires that whatever processes are operating happen to produce equilibrium that maintains constant fraction, rather than allowing population to grow or decline. Alternative mechanism that doesn't involve ejection requires identifying what that mechanism is and explaining why it produces the observed population without requiring gradual accumulation. Either way, you're adding complexity to the model, adding requirements that aren't obviously met by known processes, making the explanation less natural and more contrived. And this is a pattern we see repeatedly when examining hypervelocity phenomena. Natural explanations work in principle, can be constructed using known physics, can account for individual observations through careful application of gravitational dynamics or explosive events or other energetic processes. But when you examine population statistics, when you look at distributions and correlations and evolutionary trends, the natural explanations struggle, require special circumstances, require coincidences, require mechanisms that aren't observed elsewhere or that produce effects we don't detect, become increasingly baroque as observations accumulate and as each new constraint has to be accommodated through additional assumptions. The artificial hypothesis takes a different approach. It doesn't try to explain how natural processes accidentally produce velocities and distributions that seem improbable. Instead, proposes that the velocities and distributions reflect deliberate engineering, reflect civilizations with capability to move stars intentionally, reflect galaxy that's more populated with intelligence than we've assumed, and where some fraction of stellar motions are controlled, rather than all being natural. And that framework, that acceptance that not everything we observe is natural, changes what predictions you make and what patterns you expect to see. If civilizations can move stars, if stellar engines are real technology that advanced societies build and operate, then the distribution of hypervelocity stars depends not on where natural ejection mechanisms are strongest, but on where civilizations choose to relocate stars. Depends on cultural and strategic decisions about which stellar systems are worth moving and where they should be moved to. Depends on factors we can't predict, because we don't know the motivations or the limitations or the long-term plans of civilizations millions of years more advanced than us. But we can make some general predictions. Would expect hypervelocity stars to show trajectories that make sense as deliberate relocations rather than as random ejections. Would expect origins to cluster in regions that might be desirable starting points like star-forming regions where young systems are abundant. Would expect destinations to cluster in regions that might be desirable endpoints like outer galaxy, where collision rates are low and where development might proceed undisturbed. Would expect some fraction to show ongoing control through trajectory adjustments or through velocity changes that indicate active propulsion rather than ballistic motion, and we can look for these signatures, can examine the hypervelocity star population for patterns that would distinguish natural from artificial, can search for evidence that some fraction are being controlled, can evaluate whether the observations are more consistent with random ejection or with deliberate relocation, can test the artificial hypothesis through the same rigorous observational methodology that we apply to natural hypotheses, can take the question seriously rather than dismissing it as speculation unworthy of investigation. But the scientific establishment largely refuses to do this, refuses to seriously investigate artificial possibilities even when natural explanations are clearly struggling, maintains that everything observed must have natural origin until proven otherwise with standards of proof that are deliberately set high enough to be essentially unachievable through remote astronomical observation, creates environment where researchers who want to investigate artificial hypotheses risk their careers and their credibility by asking questions that are treated as illegitimate regardless of how much evidence supports taking them seriously. And that refusal, that institutional resistance to considering possibilities that challenge comfortable assumptions about cosmic isolation, is exactly what prevents us from recognizing what might be the most significant discovery in human history if even one of these hypervelocity stars turns out to be artificial. The velocities involved create immediate questions about what propulsion technology could achieve such performance, because accelerating a star to 1,055 kilometers per second isn't trivial engineering challenge. Stars are massive. Our Sun contains 99.86% of the total mass in the solar system, has mass of roughly 2 times 10 to the 30th power kilograms. That's 2 followed by 30 zeros. That's million tons. And changing velocity of something that massive requires applying enormous forces over extended periods, or requires achieving thrust levels that exceed anything we can currently imagine building. But the physics isn't impossible, isn't requiring violation of known laws or invocation of exotic processes beyond our understanding, is just requiring scaling, requiring that propulsion systems be built at sizes and power levels that dwarf anything humanity has achieved but that aren't prohibited by fundamental constraints. And engineers have actually designed such systems, have worked out the details of how you could move a star if you had the technological capability to build the necessary infrastructure, have created proposals that show it's possible in principle, even if we're centuries or millennia away from being able to implement them ourselves. The Kaplan thruster represents one approach, named after Matthew Kaplan of Illinois State University who published the design. It's what's called a Shkadov thruster combined with a stellar engine. The concept uses the star's own energy to provide thrust, builds enormous structures that collect stellar radiation and that channel stellar material in ways that create net force, accelerating the entire stellar system in desired direction. Doesn't require carrying propellant because the star provides effectively unlimited supply, doesn't require external power source because the star generates more energy than the thruster could ever use. Just requires building infrastructure large enough and robust enough to handle the extreme conditions and the vast scales involved. The basic mechanism is bussered ramjet operating on stellar material. Ram scoops collect matter from the stellar wind, or from material lifted directly from stellar surface. That matter gets ionized, gets converted to plasma, and then gets accelerated through electromagnetic fields to create thrust. The acceleration comes from the momentum change as material is expelled at high velocity. And because you're continuously collecting new material from the star itself, you never run out of propellant. The star is simultaneously fuel source and payload, is both what you're trying to move and what provides the energy and material to move it. The numbers are staggering but achievable. Kaplan's design requires processing roughly 1 trillion kilograms of stellar material per second. That sounds impossible until you realize that the Sun loses roughly 4 million tons per second, just through the solar wind and through conversion of mass to energy via fusion. Natural processes are already moving material at scales that dwarf what the thruster requires. The engineering challenge isn't creating material flow, but directing it, channeling it, using it efficiently to produce thrust rather than just letting it disperse randomly as natural processes do. And the thrust that such a system could produce, while tiny compared to the stellar mass, is sufficient to achieve significant velocities over timescales that are short compared to stellar lifetimes. The acceleration is roughly 10 to the negative 9th meters per second squared. That's billionth of a meter per second squared. That's pathetic by any standard we normally use, is so small that it would be imperceptible to anyone experiencing it, would create no sensation of motion or of force, would be completely undetectable without precise instruments measuring velocity changes over long periods. But integrate that tiny acceleration over millions of years, and you get substantial velocity changes. Would take roughly 5 million years to accelerate the Sun to 200 kilometers per second using this design. Would take proportionally longer to reach higher velocities. To achieve the 155 kilometers per second that S5 HVS1 displays would require roughly 43 million years of continuous thrust at this acceleration. That sounds like impossibly long time from human perspective, where civilizations rise and fall in thousands of years, but it's less than 1% of the Sun's 10 billion year main sequence lifetime. Is brief period from stellar evolution perspective is entirely feasible timescale for civilization with institutional continuity and long-term planning capability, and the thruster could operate for roughly 100 million years before consuming significant fraction of stellar mass. Could move the star 10 parsecs, roughly 33 light-years, in 1 million years of operation. Could achieve velocities approaching significant fraction of the speed of light if you were willing to run it long enough, and if you accepted the mass loss that extended operation would entail. Could theoretically accelerate to speeds that would allow intergalactic travel, though the timescales would be enormous, and the stellar evolution effects would become significant concern as you remove substantial mass from the star. But more efficient designs exist. The Kaplan thruster was deliberately conservative design, using straightforward physics and avoiding exotic assumptions. But if you're willing to accept more advanced technology, if you assume capabilities beyond what near-term human engineering might achieve, you can improve performance substantially. The Savoy Star Tug combines aspects of the Kaplan engine with Shkadov thruster in configuration that's more efficient and that achieves higher accelerations and maximum velocities. The Shkadov thruster is partial Dyson sphere, is enormous curved mirror positioned near the star such that it reflects stellar radiation back toward the star in specific direction. The reflection creates imbalance in radiation pressure. The star emits light equally in all directions naturally. The mirror reflects portion of that light back. The net effect is that star experiences force in direction opposite to the mirror, is pushed away from the mirror by its own radiation pressure, and because the mirror is gravitationally bound to the star, because it orbits the star maintaining fixed position relative to stellar surface, the entire system accelerates together. The advantage of Shkadov thruster is that it requires no material processing, doesn't need to collect and ionize and accelerate stellar wind, just needs to reflect light. Just needs mirror that can withstand the thermal environment and that's large enough to intercept significant fraction of stellar output. The disadvantage is that the thrust is extremely low, radiation pressure from starlight is weak force. Even when you're reflecting substantial fraction of stellar luminosity, you're producing accelerations that are tiny, even by the already tiny standards of stellar engines. The Savoy Star Tug improves on this by combining the reflection approach with material collection and ejection, uses the mirror to collect stellar energy and to provide some thrust through radiation pressure, but also lifts material from the star and accelerates it to create additional thrust from momentum exchange. And crucially, it positions the thruster in front of the star rather than behind it. Pulls the star through gravitational attraction rather than pushing it from behind through direct force. This might sound like distinction without difference, but it matters for efficiency. When you push from behind, you're fighting against stellar gravity trying to recapture any material you eject. When you pull from in front, you're using stellar gravity to help accelerate the material away from the star after you've processed it. The gravitational assist increases the effective exhaust velocity, which increases the thrust for given mass flow rate, which improves the overall efficiency of the system. The result is that Savoy Star Tug can potentially achieve accelerations several times higher than Kaplan thruster, using the same mass flow and power levels. And at maximum efficiency, operating for extended period and accepting substantial stellar mass loss, it could theoretically accelerate a star to 27% of the speed of light before running out of material. That's 80,000 kilometers per second. That's 45 times the velocity of S5 HVS1. That's speed that would let you cross the galaxy in few 100,000 years. That's genuinely intergalactic travel capability, where you could reach Andromeda in 10 million years or so. So the engineering is possible, the physics works, the designs exist showing how you could build stellar engines if you had the industrial capacity and the materials and the coordination to construct infrastructure at the scales required. The question isn't whether it's physically possible to move stars, the question is whether anyone has actually done it. Whether the hypervelocity stars we're observing are natural phenomena, or whether some fraction represents artificial relocations executed by civilizations with these capabilities. and examining that question requires looking for signatures that would distinguish natural from artificial, requires identifying observable features that would be present if stellar engines are operating, but absent if velocities are achieved through natural ejection mechanisms, requires careful analysis of stellar properties and trajectory characteristics and population statistics, looking for patterns that theory predicts should exist if engineering is involved. The most obvious signature would be ongoing control. Would be trajectory adjustments indicating that the star's motion is being actively managed, rather than following ballistic path determined by initial ejection event. Natural ejection from supermassive black hole imparts velocity but doesn't provide continued acceleration. The star follows gravitational trajectory afterward, with velocity gradually decreasing as it climbs out of galactic potential well. Should show smooth deceleration that matches what gravitational models predict given the stellar mass and the galactic mass distribution. Artificial propulsion could show different behavior, could show continued acceleration as thruster operates, could show velocity changes that don't correspond to gravitational effects, could show trajectory corrections that optimize path towards specific destination rather than just following whatever direction initial ejection happened to provide, could demonstrate intelligence in how motion evolves rather than showing passive response to gravity. Detecting these signatures requires precise astrometry over extended periods, requires measuring stellar positions accurately enough to determine velocities to better than kilometer per second precision, requires tracking motion over years or decades to detect accelerations or trajectory changes that indicate ongoing propulsion, requires exactly the kind of long-term monitoring that major survey programs like Gaia are providing, but that needs to be sustained and extended to build baselines long enough that subtle effects become detectable, and we're starting to do this. Starting to accumulate astrometric data that could reveal whether hypervelocity stars are under control, starting to have the precision and the temporal coverage needed to test whether velocities are changing in ways that natural trajectories shouldn't produce, starting to be able to distinguish between ballistic motion and powered flight at stellar scales. But the analysis needs to be done with artificial hypothesis in mind. Needs to be looking for control signatures deliberately rather than just assuming everything is natural and interpreting any apparent anomalies as measurement uncertainties or modelling errors. The stellar properties themselves might provide clues, because if you're going to invest the enormous resources required to build stellar engine and operate it for millions of years, you probably have reasons for choosing which stars to move, have criteria for what makes good relocation candidate versus what should be left in place. And those criteria might be detectable in the population of hypervelocity stars if we look for correlations that natural ejection wouldn't produce. Young stars might be preferred targets because they have longer remaining lifetimes. Because if you're investing millions of years in relocating a stellar system, you want the star to remain viable for billions of years after relocation completes. Moving old star that's approaching end of its main sequence life doesn't make much sense unless there are compelling reasons to do so. So if hypervelocity population is enriched in young stars compared to the general stellar population, if the age distribution skews young in ways that natural ejection mechanisms wouldn't produce, that's suggestive of selection criteria consistent with deliberate relocation. Metal-poor stars might be avoided because they formed from pristine gas that hasn't been enriched by previous generations of stellar nucleosynthesis. They're less likely to have rocky planets with the elements needed for complex chemistry and biology and technology. If the goal of relocation is to move inhabited systems or potentially habitable systems, then metal-poor stars are less interesting targets. So if hypervelocity population is enriched in metal-rich stars, if the metallicity distribution differs from what natural ejection would produce, that's another potential signature of selection. Binary and multiple star systems might be treated differently from single stars, depending on whether the propulsion technology can handle the complexities of moving bound stellar systems versus just individual stars. Natural ejection specifically targets binaries because that's how the Hill's mechanism works. Tidal forces tear binaries apart and eject one member. So natural hypervelocity population should be dominated by single stars that were previously in binaries. Artificial relocation might show different pattern, might include both singles and binaries if technology allows moving complete systems, might show excess of singles if binaries are deliberately avoided because they're harder to move. Examining these population characteristics requires careful statistical analysis, comparing hypervelocity stars to control populations and determining whether differences are significant or whether they're consistent with natural variation and selection effects. Requires controlling for observational biases where certain types of stars are easier to detect than others. Requires building large enough samples that statistical power is sufficient to detect modest effects rather than just the most dramatic differences. Requires exactly the kind of rigorous comparative study that should be standard procedure when evaluating whether population shows signatures of artificial selection. But again, this analysis largely isn't being done because the artificial hypothesis isn't taken seriously enough to motivate the investigation. Because asking whether hypervelocity stars show evidence of deliberate selection is treated as fringe question rather than as legitimate scientific inquiry. Because the default assumption is that everything is natural and that looking for artificial signatures is waste of time better spent on conventional questions. And that default assumption, that refusal to seriously investigate artificial possibilities, is exactly what ensures we won't recognize artificial phenomena even when evidence is available if we just bothered to look. The planetary systems associated with hypervelocity stars provide another crucial test case. Because natural ejection through Hill's mechanism should destroy planetary systems. The tidal forces that tear binary apart, that accelerate one star to escape velocity while capturing the other, are far stronger than the gravitational binding between star and planets, should strip planets away, should leave hypervelocity star without planetary companions because anything that was orbiting it couldn't maintain orbit through the violent disruption that ejection event represents. But we've found at least one hypervelocity star that has planet. That shows the wobble and the periodic variations that indicate planetary companion remains in orbit despite the star travelling at velocity sufficient to escape the galaxy. And that's profoundly difficult to explain through natural ejection. Through any process that applies forces strong enough to accelerate star to hypervelocity while leaving planetary system intact, the gravitational hierarchy doesn't allow it. The tidal disruption that creates the velocity should tear apart anything that's not gravitationally bound more strongly than the planet is to the star, yet the planet survived, remains in orbit, demonstrates that whatever accelerated this star to hypervelocity didn't apply the kind of impulsive tidal forces that Hill's mechanism requires, didn't subject the system to disruption that would strip planets, instead must have involved gentler acceleration. Gradual velocity change applied over timescale long enough that planets could adjust their orbits and remain bound rather than being torn away by sudden force. And that gentleness, that gradual acceleration characteristic is exactly what stellar engine provides, but what natural ejection doesn't. When you use thruster that operates over millions of years, when acceleration is billionth of a meter per second squared applied continuously, rather than being sudden velocity kick from close encounter with supermassive black hole, planetary systems can survive, can adapt, can maintain orbits that slowly evolve as the entire system accelerates, but that don't experience disruption that would unbind them. So finding hypervelocity star with planet is evidence that challenges natural explanation while supporting artificial, is observation that Hill's mechanism struggles to account for but that stellar engine naturally predicts, is exactly the kind of data point that should motivate serious investigation of artificial hypothesis, rather than being dismissed as puzzling anomaly that must somehow have natural explanation we just haven't identified yet. The case of Barnard's star brings the artificial hypothesis uncomfortably close to home, because Barnard's star isn't just any high-velocity object in some distant region of the galaxy, is the second closest stellar system to our Sun, is located just 6.3 light-years away in the constellation Ophiuchus, is visible through modest telescopes from Earth's northern hemisphere, is object we've been studying intensively for over a century because its proximity makes it ideal target for characterizing nearby stellar environment and searching for planetary systems around red dwarfs, and Barnard's star is moving fast, not hypervelocity in the strict sense, not travelling at speed sufficient to escape the galaxy entirely, but moving substantially faster than any other star in our local neighbourhood, is travelling at roughly 142 km per second relative to the Sun. Compare that to typical stellar velocities in the solar neighbourhood of 20 to 30 km per second. Barnard's star is moving at 4 to 5 times the normal speed, is carrying velocity that's intermediate between typical stellar motions and the genuine hypervelocity objects that are escaping the galaxy. And its trajectory is intriguing. When you backtrack the motion, when you calculate where Barnard's star was in the past, the origin appears to be in the direction of the Large Magellanic Cloud. Same region where several of the confirmed hypervelocity stars seem to originate. Same direction that creates problems for natural explanation, because we can't identify supermassive black hole in the LMC that could produce the necessary ejection velocities. Barnard's star might be another example of whatever mechanism is operating in that region, might be related to the hypervelocity population, even though it's travelling at lower velocity. But what makes Barnard's star especially interesting is the anomalies that careful observation has revealed, because this isn't just fast-moving red dwarf following predictable trajectory. Is object showing behaviours that are difficult to explain through natural stellar processes, that create questions about whether everything we're observing is actually natural, or whether some of it might indicate artificial activity. The wobble is the most persistent mystery. Astrometric measurements show that Barnard's star doesn't move in straight line, shows periodic variation in position that indicates something is gravitationally perturbing it, that something massive is orbiting the star and causing it to wobble as the star and the companion orbit their common centre of mass. This is how we detect exoplanets, is standard technique that's discovered hundreds of planetary systems through the wobble they induce in their parent stars, and the wobble amplitude for Barnard's star suggests something substantial is present, something with enough mass to create detectable perturbation despite the star being relatively nearby where our measurement precision is highest. Multiple teams have claimed planetary detections based on this wobble, have announced discoveries of super-Earths or small Neptune mass objects orbiting at various distances, have published results suggesting Barnard's star has planetary system that we should be able to characterize in detail given the proximity and the measurement quality. But every one of these detections has been retracted, has failed confirmation when additional data was collected or when analysis methods were refined, has turned out to be artifact of stellar activity or instrumental systematics or statistical noise that looked like planetary signal but that disappeared when examined more carefully. And yet the wobble persists. The variations in stellar position remain visible in the data. Something is clearly affecting the star's motion in ways that suggest gravitational perturbation from companion that observations keep failing to confirm. Small planets have been confirmed. Objects with masses of few Earth masses orbiting at distances where they'd be frozen ice worlds, receiving minimal stellar radiation. But these confirmed planets are too small to explain the wobble, don't have sufficient mass to create the astrometric signature that's being detected. Leave the primary anomaly unexplained even though they demonstrate that Barnard's star does have planetary system of some kind. So what's causing the wobble if not planets massive enough to account for it? Brown dwarf companion has been ruled out through infrared surveys that would have detected such object if it existed. Stellar companion would be visible directly and isn't seen. Black hole companion would create other observable effects beyond just the astrometric wobble, and none of those effects are detected. Natural explanations keep being proposed and keep failing to fully account for observations, but artificial explanation is never seriously considered. Possibility that the wobble might be caused by massive structure in orbit around the star, structure that doesn't emit light the way planet or brown dwarf would, structure that might be present for purposes we can't determine without better observations, that possibility is dismissed without investigation, because suggesting that nearby star might have artificial structure massive enough to create astrometric wobble is treated as beyond the pale, even though it's physically possible, and even though natural explanations keep failing. The flare activity compounds the mystery, because Barnard's star is old red dwarf, has age estimated at 7 to 12 billion years based on kinematics and metallicity, is substantially older than the Sun, and red dwarfs of this age should be quiescent, should have exhausted their magnetic activity, should be quiet stars that don't produce significant flares or variability because the dynamo processes that generate stellar magnetic fields have wound down over billions of years of evolution. Yet in 2021, Barnard's star produced massive flare, brightened by factor of several in matter of hours, emitted high-energy radiation at levels completely inconsistent with quiescent old red dwarf, demonstrated activity that young active stars show, but that objects of Barnard's age shouldn't exhibit, and the flare wasn't subtle anomaly that might be dismissed as measurement error, was dramatic event captured by multiple instruments, was undeniable demonstration that this star is more active than it should be given its age and properties. Natural explanations for the flare exist. differential rotation in stellar interior could generate magnetic field even in old star if conditions are right. Interaction with planetary magnetic fields could possibly trigger stellar activity, though the mechanism isn't well understood and would require planetary magnetic fields far stronger than anything we observe in solar system. Accretion of material from interstellar medium could potentially inject energy, though the required accretion rates would be detectable through other means and aren't observed. But each natural explanation requires special circumstances, requires Barnard's star to be unusual in ways that aren't obviously true for other similar stars, requires invoking processes that we don't observe directly, but that must be operating to account for the flare, stacks assumptions in ways that make the explanation less natural and more contrived. An artificial explanation is never mentioned. Possibility that the energy release might not be stellar flare at all, but might be artifact of activity in orbit around the star, activity from structures or systems that we can't detect directly, but that occasionally produce emissions we can observe. That possibility is treated as too speculative to investigate. And the combination of anomalies is what makes Barnard's star so intriguing as potential artificial candidate. The high velocity suggesting it might be relocated system, the trajectory connecting it to region where other anomalous velocity objects originate, the unexplained wobble indicating massive presence that doesn't match any natural companion, the flare activity inconsistent with stellar age and properties. Each individually might be explicable through exotic but natural processes, but collectively they create patterns suggesting this nearby system might not be entirely natural, might be example of stellar engineering that we're failing to recognize because we refuse to seriously consider the possibility. And the proximity creates obvious speculation about connection to UAP phenomenon. Because if there's artificial infrastructure at Barnard's star, if the system has been relocated by civilization with stellar engine technology, if the wobble indicates massive structures in orbit that we can't see with current instruments, then that civilization is our nearest neighbor, is roughly 6 light-years away, is close enough that radio signals from Earth would have reached them decades ago, is close enough that if they have capability to visit other stellar systems, they could reach us on timescales that are short compared to stellar lifetimes. We've been broadcasting electromagnetic signals into space since the 1920s, when radio technology became widespread, have been unintentionally announcing our presence to any civilization within roughly 100 light-years that has receivers sensitive enough to detect artificial signals against natural cosmic radio background. Barnard's star is well within that radius. If inhabited system exists there, if technological civilization is present, they've known about us for roughly 90 years, have had time to observe our technological development, have had time to decide whether we're interesting enough to visit or whether we should be left alone to develop without interference. And the UAP observations that have accumulated over past 80 years, the aircraft carrier-sized objects maneuvering in ways that violate our understanding of aerodynamics and propulsion, the transmedium vehicles that transition seamlessly between air and water, the objects displaying accelerations that would destroy any craft we could build, all of this could potentially be explained as visiting vehicles from nearby civilization that has been monitoring our development since detecting our radio emissions. That's speculation. Is connecting observations through hypothesis that can't be proven without additional evidence. But it's speculation grounded in physical possibility rather than in violation of known physics. If Barnard's star has advanced civilization, if that civilization has technology to move stars and to build massive orbital structures and to visit other stellar systems, then monitoring nearby emerging technological species is exactly what you might expect them to do. And the observed UAP characteristics match what you'd expect from vehicles designed for interstellar travel capability, match better than they match any known human technology or any natural phenomena that's been proposed as explanation. But mainstream science won't connect these dots, won't seriously investigate whether UAP observations might be related to potential artificial activity at nearby stellar system, won't examine whether the Barnard star anomalies and the hypervelocity star population and the intergalactic star distribution might all be evidence of the same underlying phenomenon, which is that the galaxy is substantially more populated with technological civilization than we've been assuming. Instead treats each anomaly as separate puzzle, requiring separate natural explanation, rather than recognizing that unified artificial framework might explain multiple observations more simply than fragmented collection of exotic natural processes. The pulsar systems provide another class of potential stellar engine candidates. Because pulsars are neutron stars with extremely strong magnetic fields that emit beams of radiation from their magnetic poles. And if the beam happens to point toward Earth as the neutron star rotates, we see pulses of radio emission at precise intervals determined by the rotation period. This makes pulsars exceptionally accurate natural clocks, makes them ideal objects for testing physics under extreme conditions, makes them valuable for timing applications and for gravitational wave detection, and for all sorts of astrophysical investigations. But pulsars in binary systems with ordinary stars show interesting behaviors that might not be entirely natural. The strong magnetic fields and the intense radiation from the pulsar interact with the companion star, strip material from the companion surface, create accretion streams that flow from the normal star toward the neutron star, generate X-ray emission as the material impacts the neutron star surface, create all sorts of observable phenomena that reveal details about the binary system and about how matter behaves under extreme conditions. And in some cases, those interactions might provide thrust. The magnetic fields could channel material ejection in specific directions, could create asymmetric mass loss that produces net force on the binary system, could function as natural stellar engine where the pulsar's magnetic activity drives the motion of both stars, could achieve accelerations and velocities that wouldn't occur for isolated systems without active propulsion. PSR JSIS 959 Pluto-2048 is binary pulsar system, showing exactly this kind of behavior. The pulsar is in tight orbit with normal stellar companion. The system is moving at substantial velocity through the galaxy. And detailed observations suggest the motion might not be entirely ballistic, might show trajectory evolution consistent with ongoing thrust from the pulsar-companion interaction, might demonstrate control where the magnetic field configuration is being adjusted to optimize thrust direction, might be example of stellar engine using natural pulsar as power source, but with control systems managing the thrust to achieve desired trajectory. That's speculative interpretation, is reading intentionality into observations that could potentially be explained through complex but natural astrophysical processes, but its interpretation grounded in engineering principles. If you had pulsar in binary system, and if you wanted to use it to move the binary to different location in galaxy, manipulating the magnetic field to control mass ejection from companion is exactly how you do it, is optimal approach using natural energy source rather than requiring you to build separate propulsion infrastructure. And looking for this signature in other pulsar binaries, examining whether trajectory patterns suggest control versus random motion, testing whether the population shows characteristics consistent with deliberate relocation versus natural distribution. All of this is investigation that could be done but that isn't being pursued, because artificial hypothesis is dismissed before examination occurs. Because even when we observe phenomena that look engineered, we default to natural explanation and never test whether artificial interpretation might actually fit observations better. The supernova hypothesis represents another attempt to explain hypervelocity stars without invoking supermassive black holes. Because supernovae are powerful events, release enormous energy in matter of seconds as massive star collapses and rebounds in catastrophic explosion. And if supernova occurs in binary system, if one star explodes while companion remains intact, the energy could potentially accelerate the companion to extreme velocity as it receives asymmetric kick from the explosion. But the physics is challenging. The energy needs to be transferred efficiently to the companion, needs to be directed in ways that create coherent velocity boost rather than just heating and disrupting the companion, needs to account for the fact that supernova explosions are roughly spherically symmetric despite some asymmetries from rotation and magnetic fields. Achieving the extreme velocities that hypervelocity stars display requires very specific conditions that make the mechanism rare at best, and recent observations have complicated the supernova explanation further, because some hypervelocity stars show chemical compositions that don't match what you'd expect from objects that experience close supernova, don't show the unusual abundances that contamination from supernova ejecta would produce, don't show evidence of having been processed through the high-energy environment that close supernova would create, look like normal stars that achieved their velocities through mechanisms that didn't involve being bathed in supernova radiation and ejecta. So supernova mechanism, like supermassive black hole mechanism, works in principle but struggles to explain the observed population, can account for some examples but can't be dominant source for most hypervelocity stars, leaves majority of the population requiring alternative explanations, And when you've eliminated or severely constrained both of the obvious natural mechanisms, when neither black hole ejection nor supernova acceleration appears adequate to explain most observations, you should be looking seriously at alternative frameworks, rather than just assuming that some other natural mechanism we haven't identified yet will eventually be discovered. The stellar engine designs that engineers have developed aren't just theoretical exercises, aren't just thought experiments about what might be possible in principle, are serious engineering proposals that have been analysed in detail to verify that the physics works and that the structures could be built using materials and technologies that don't require violating known physical laws. Are designs that show how civilizations more advanced than us could actually move stars if they chose to invest the resources required, and the designs keep getting refined, keep getting improved as engineers identify more efficient approaches, or find ways to reduce required infrastructure mass, or develop better methods for managing the extreme thermal and radiation environment near stellar surfaces. The Kaplan thruster was published in 2019. The Savoy Star Tug was proposed in 2020. Additional variants and improvements have been published since. The engineering community is actively working on these concepts, even though we're nowhere near being able to build them ourselves. And that activity, that continued refinement of stellar engine designs, demonstrates that the concepts are taken seriously, at least in engineering contexts, even if astronomical community refuses to consider that they might already exist. Shows that there's no fundamental barrier preventing construction of such systems. Shows that we can work out the details precisely enough to demonstrate feasibility. Shows that when humanity reaches sufficient technological capability, we could build stellar engines ourselves if we decided the benefits justified the investment. So the question isn't whether stellar engines are possible. The question is whether anyone else has built them, whether we're first to conceive these concepts, or whether we're late to recognizing engineering capabilities that others achieved long ago, and that they've been using to reshape galactic stellar distribution in ways we're only now beginning to notice, because our observations have finally reached the precision and coverage needed to detect the signatures. The motivations for moving stars might seem obscure from human perspective, where the scales involved are so vast and the timescales so long that the entire concept feels abstract. But from the perspective of civilization with institutional continuity measured in millions of years, from species that thinks on timescales where stellar evolution matters and where galactic dynamics are relevant to planning, the reasons become clearer. And understanding those motivations, recognizing why advanced civilization might choose to invest in stellar engine technology, provides context that makes the artificial hypothesis more plausible rather than seeming like wild speculation. The most obvious motivation is stellar system relocation for safety or optimization purposes. Stars don't remain in fixed positions in the galaxy, orbit the galactic center on paths that take millions of years to complete, but that inevitably bring stars into close encounters with other stars, with molecular clouds, with all the hazards that exist in galactic disk where stellar density is relatively high, and where collisions or near misses are statistically inevitable over long enough timescales. If you're civilization that wants to ensure long-term survival, if you're planning on timescales where these encounters become relevant concerns, relocating to safer region of the galaxy is rational strategy. The galactic halo, the spherical distribution of stars that surrounds the galactic disk, offers substantially lower collision rates. Stars in the halo are more widely separated. Move on orbits that don't intersect the dense regions where most stellar formation occurs and where most supernova explosions happen. Experience quieter environment where long-term development could proceed with minimal risk of catastrophic disruption from external events. If you could move your stellar system from the disk to the halo, you'd be trading the rich stellar neighborhood and potential interaction with other civilizations for isolation and safety. And achieving that relocation requires exactly the kind of velocities that hypervelocity stars display. Requires accelerating to speed sufficient to escape the gravitational potential of the galactic disk and reach the halo regions. Requires sustained thrust over millions of years to achieve the necessary velocity change. Requires stellar engine. And if this is common motivation, if many advanced civilizations decide that halo relocation is desirable strategy, then you'd expect to see population of stars moving from disk toward halo at velocities that appear anomalous from natural perspective, but that makes sense as deliberate relocations. The intergalactic relocation represents even more extreme version of this strategy. If you want absolute isolation, If you want to guarantee that no external events could possibly threaten your civilization's survival, leaving the galaxy entirely achieves that goal. The space between galaxies is empty, contains no stars that could pose collision hazards, no supernovae that could sterilize your planets with radiation, no molecular clouds that could disrupt your stellar system, nothing except the cosmic background radiation and the expanding space itself, ultimate safe haven for civilization that values security over all other considerations. But intergalactic relocation comes with costs. You're giving up access to resources that galactic environment provides, giving up potential interactions with other civilizations, giving up the possibility of utilizing galactic infrastructure if such infrastructure exists, accepting that you'll be isolated for timescales measured in millions or billions of years with no possibility of contact or trade or cultural exchange. That's sacrifice that might be acceptable for some civilizations, but that others might reject as too extreme. The resource access motivation provides different rationale for stellar relocation, because while stars are roughly similar in many ways, they vary in metallicity, in chemical composition, in the abundance of elements heavier than hydrogen and helium, and those differences matter for technological applications. Metal-rich stars are more likely to have rocky planets, are more likely to have systems with abundant heavy elements needed for industrial processes, are more desirable as targets for settlement or development if you're civilization that values resource availability. So if you formed in metal-poor environment, if your original stellar system has low metallicity that limits available resources, relocating to metal-rich region makes strategic sense, achieves access to materials that aren't abundant in your home system, and the required velocities depend on where you're starting and where you want to go, but could easily reach ranges that make the star appear as hypervelocity object during the transit, even though the ultimate destination is another location within the galaxy, rather than escape to intergalactic space. The stellar evolution timeline creates urgency for certain types of relocation, because stars don't maintain constant properties throughout their lives. Evolve through sequence of phases with different characteristics and different habitability implications. The Sun is currently in stable main sequence phase, where it's been for roughly 4.5 billion years and where it will remain for another 5 billion. But eventually it will exhaust hydrogen in its core and begin evolving toward red giant phase, where it expands dramatically and where inner planets become uninhabitable or are consumed entirely. If your civilization developing in stellar system that's approaching the end of its main sequence lifetime, if you're facing the inevitable transformation that will make your current home uninhabitable, relocating the entire stellar system to younger star is an appealing option, achieves continuity, allows you to maintain your existing infrastructure and ecology and civilization structure, rather than having to abandon everything and rebuild from scratch around different star. And if you have stellar engine technology that makes such relocation possible, using it to avoid the forced migration that stellar evolution would otherwise require is rational choice. But the timing is interesting, because you don't want to wait until the star is already evolving off the main sequence. Want to relocate while it's still stable, and while you have billions of years remaining before evolution forces the issue, which means civilizations might be relocating stars that from our perspective appear to have plenty of remaining lifetime, might be showing velocities that seem unnecessary from natural perspective, but that makes sense as proactive strategy implemented long before it becomes urgent necessity. The galactic ecology perspective suggests yet another class of motivations that might drive stellar relocation. Because if the galaxy contains many civilizations operating on similar timescales and with similar capabilities, if stellar engineering is common practice rather than rare achievement, then the collective effects of many civilizations making independent relocation decisions could create large-scale structure in stellar distributions, could create patterns that appear natural when examined locally, but that reveal design when analyzed statistically across the entire galaxy. For example, if younger civilizations tend to relocate toward the halo for safety, while older civilizations might return to the disk for resource access or for interaction with emerging species, you'd see bidirectional flow with net rates depending on the balance between outward relocating and inward returning populations. If certain metallicity ranges are preferred, because they balance resource availability against stellar stability, you'd see concentration of stellar systems in those metallicity zones beyond what natural chemical evolution would produce. If coordination exists among civilizations, if there are agreements or norms about which regions should be developed versus which should be preserved as nature reserves or as zones for emerging species, you'd see systematic avoidance of certain areas and concentration in others. All of these effects would create structure in stellar distributions and kinematics that would be difficult to explain through purely natural processes, but that would make sense as collective result of many independent civilizations making decisions according to similar criteria. Testing these predictions requires looking at stellar distributions and velocities across the galaxy, rather than just focusing on individual hypervelocity examples. Requires statistical analysis comparing observations to both natural models and to models incorporating artificial relocation. Requires building simulations that show what galaxy would look like if significant fraction of stellar systems have been relocated versus what it would look like if all stellar motions are natural. And then comparing those simulations to actual observations to determine which framework better matches what we see. That work has been done to some extent for natural models. We have detailed simulations of galactic dynamics showing how stellar populations evolve under gravitational forces, how spiral arms form and dissolve, how stellar streams result from galaxy mergers and tidal disruption, how velocity distributions depend on stellar age and location, all grounded in well-understood gravitational physics and validated against observations. But the artificial models haven't been developed seriously, haven't been simulated with same rigor because the hypothesis isn't taken seriously enough to justify the computational investment. We don't have predictions for what galactic stellar distributions would look like if 10% or 1% or even 0.1% of stellar systems have been artificially relocated. Don't have the baseline that would let us test whether observations are more consistent with pure natural evolution or with mixed natural plus artificial dynamics. Building those models is technically feasible, is just computational astrophysics exercise that could be done if resources were allocated and if researchers were willing to work on question that might be perceived as fringe, would provide quantitative framework for evaluating artificial hypothesis rather than leaving it as qualitative speculation, would enable proper statistical comparison determining whether incorporating artificial relocations improves fit to observations or whether natural-only models are adequate. The detectability of active stellar engines provides another avenue for investigation, because while stars that have already been relocated and are now coasting on ballistic trajectories might be difficult to distinguish from natural hypervelocity objects, stars that are currently under thrust, that have active propulsion systems operating, should show distinctive signatures that observations could detect if we knew what to look for and if we searched systematically. The most obvious signature is ongoing acceleration. Stars under thrust should show velocity changes over time that don't match what gravitational dynamics predict. Should be speeding up or slowing down or changing direction in ways that indicate forces are being applied beyond just gravity. Detecting this requires precise astrometry over extended periods, but is within our technical capability for relatively nearby stars where position measurements can achieve the precision needed to detect accelerations on order of what stellar engines produce. The thermal signature provides another potential indicator, because stellar engines process enormous amounts of material and energy, create waste heat that has to be radiated, might show infrared excess beyond what the stellar blackbody spectrum predicts, might emit at specific wavelengths that indicate artificial processing rather than natural stellar phenomena, might show variability patterns that correlate with thrust operations rather than with natural stellar activity. Spectroscopic anomalies could reveal material processing. If the thruster is collecting stellar material and ionizing it and accelerating it to create thrust, the spectral lines might show velocities and ionization states that don't match what natural stellar winds produce, might show asymmetries indicating directed flows rather than roughly spherical expansion, might show composition variations if the thruster is selectively processing certain elements over others for efficiency reasons. Polarization of stellar light might indicate large structures near the star. Because mirrors or collectors needed for Shkadov thruster configurations would create polarization through reflection and scattering that natural stellar surfaces don't produce. Monitoring polarization as star rotates might reveal structures orbiting the star that aren't visible directly, but that affect the polarization state of transmitted light. Radio emissions might indicate power systems or control systems, because maintaining stellar engine requires enormous computational capability for monitoring and adjusting thrust and managing all the subsystems. That computation requires power and produces electromagnetic emissions that might be detectable if we search at appropriate frequencies, might show modulation patterns that indicate artificial signal processing rather than natural astrophysical processes. All of these signatures are searchable with current or near-future technology, require dedicated observation programs and systematic surveys rather than just opportunistic observations, require taking the artificial hypothesis seriously enough to design observations that could detect evidence if it exists, require astronomers being willing to look for these signatures without fear that doing so will damage their credibility or will be perceived as waste of telescope time on fringe speculation. The SETI paradigm shift that recognizing stellar engines would represent extends beyond just confirming that technological civilizations exist. Extends to recognizing that advanced civilizations operate on scales and timescales completely different from what human experience prepares us to expect. That their technology isn't just faster spacecraft or better computers, but is planetary scale or stellar scale engineering that reshapes their environments in ways that are visible across interstellar distances and that persist for millions of years. Traditional SETI searches for radio signals assumes that technological civilizations will be broadcasting, either deliberately or inadvertently, and that detecting those broadcasts will provide first evidence of their existence. That approach has been pursued for over 60 years with increasingly sophisticated instruments and with expanding search space but with zero confirmed detections. No alien radio signals, no evidence that anyone out there is trying to communicate or that their leaked transmissions are strong enough for us to detect. But stellar engines represent different SETI strategy. Instead of searching for deliberately transmitted signals that might not exist or might be too weak to detect, search for inevitable consequences of stellar-scale engineering. Search for modifications to stellar environments that advanced civilizations would create if they're manipulating their suns for propulsion or for energy collection, or for any other purpose that requires large-scale intervention. Search for techno-signatures that are byproducts of activity, rather than trying to detect intentional communication. And the advantage of this approach is that stellar engines are bright, are operating at power levels that dwarf any communication system, are creating effects that are visible across the galaxy not as faint signals requiring enormous receiving dishes, but as modifications to stellar populations that show up in standard astronomical surveys, are already in our data, are probably already detected but classified as natural phenomena, because we're not analysing observations with artificial hypothesis in mind. Reanalyzing existing surveys looking for stellar engine signatures could provide immediate results without requiring new telescopes or new observation campaigns. Just requires different analysis framework. Different questions being asked of data that's already been collected. Different statistical tests comparing stellar populations to predictions from natural versus artificial models. Different searches through catalogues looking for combinations of properties that would indicate engineering rather than nature. The Gaia mission provides perfect dataset for this reanalysis, has measured positions and velocities for over 1 billion stars with unprecedented precision, has characterized stellar properties including temperature and luminosity and chemical composition, has built comprehensive catalogue of galactic stellar population that's ideal for statistical studies looking for patterns or anomalies, and buried in that dataset might be stellar engine signatures waiting to be recognized if someone performs the analysis designed to find them. The cultural implications of confirming that stellar engines exist and that hypervelocity stars represent artificial relocations rather than natural ejections would be profound. Would force humanity to confront that we're not just potentially not alone, but that we're sharing galaxy with civilizations so advanced that they can move stars. That our technological achievement, impressive as it might seem to us, is primitive compared to what others have accomplished. That the timescales and scales on which advanced civilizations operate are so different from human experience that we can barely comprehend their perspective or their motivations. And that confrontation might be healthy, might provide perspective about our place in cosmic context that's currently missing from human self-conception. Might motivate long-term thinking that's difficult to maintain when you're a species that's been technological for only a few centuries, and that's struggling with challenges that seem urgent on human timescales, but that are trivial compared to stellar evolution or galactic dynamics. Might inspire us to think bigger about what's possible and what we might achieve if we survive long enough to develop the institutional continuity and technological capability that stellar engineering requires. But it might also be intimidating, might create sense of inadequacy or fear about what civilizations with these capabilities might do if they notice us or if they decide our development is proceeding in ways they disapprove of. Might raise questions about whether we're being observed or whether we're being deliberately isolated until we reach some threshold of technological or social development that makes us acceptable for contact. Might force us to wonder whether the galactic community, if it exists, has rules or norms or expectations about how emerging species should behave, and whether we're violating those expectations through our various planetary scale impacts. The physics denial that characterizes mainstream astronomy's response to artificial hypotheses is what's most frustrating about the current situation, because the arguments against seriously investigating stellar engines aren't based on physical impossibility, aren't claiming that the engineering can't work or that the velocities can't be achieved or that the signatures wouldn't be detectable. Instead, the arguments are sociological, are based on claiming that artificial explanations are inherently less probable than natural explanations regardless of what observations show, are invoking Occam's razor in ways that assume natural is always simpler than artificial, even when the natural explanations require stacking multiple special circumstances, while artificial explanation unifies observation straightforwardly. But Occam's razor properly applied doesn't prefer natural over artificial automatically, prefers simpler explanations over more complex ones, and if artificial stellar engines explain multiple observations that would otherwise require separate complex natural mechanisms for each, if incorporating artificial component into models actually simplifies rather than complicates the overall framework, then Occam's razor supports rather than opposes the artificial hypothesis. The burden of proof asymmetry is another manifestation of the bias against artificial explanations, where natural hypotheses are accepted provisionally even when evidence is weak or when predictions don't match observations, where researchers can propose exotic natural mechanisms and get them published and cited and incorporated into models without requiring definitive proof that the mechanisms actually operate. But artificial hypotheses are held to much higher standards, are rejected unless proof is essentially absolute, are dismissed even when evidence is suggestive because the threshold for acceptance is set deliberately high enough to be essentially unachievable, and that asymmetry prevents progress. Prevents us from recognizing artificial phenomena even when evidence is available, because we refuse to seriously investigate unless forced to by observations so clear that denial becomes impossible. Ensures that we'll be late to recognizing the truth rather than being among the first to see what the evidence is showing. Guarantees that when history judges how we responded to the possibility that hypervelocity stars might be artificial, the judgment will be that we failed to investigate properly because our biases prevented us from asking the right questions. The 21 confirmed hypervelocity stars that we've detected are almost certainly just a small fraction of the total population. Are the brightest and nearest examples that our surveys have found, but that represent only what's detectable with current instruments and observation programs. Extrapolating from detection rates and from the volume of space surveyed suggests that the total hypervelocity population in the galaxy might be millions of objects, might represent a significant fraction of all stellar systems if the artificial relocation hypothesis is correct and if stellar engineering is common practice among advanced civilizations. And as our surveys improve, as projects like Gaia continue, and as new wide-field telescopes come online, and as our ability to detect and characterize stellar velocities increases, we'll find more. We'll build larger samples that enable better statistical analysis. We'll potentially detect stellar engines that are currently operating and showing the active signatures that would distinguish them clearly from natural objects. We'll accumulate evidence that either supports or refutes the artificial hypothesis depending on what the observations actually show, rather than on what our prejudices suggest they should show. The question is whether we'll analyze that evidence honestly, whether we'll be willing to follow where the data leads even if it challenges our assumptions about cosmic isolation, whether we'll investigate artificial possibilities with same rigor we apply to natural hypotheses rather than dismissing them reflexively, whether we'll recognize that confirming stellar engines would be discovery of the century rather than treating it as an embarrassing topic that serious astronomers shouldn't discuss. Because if even one hypervelocity star turns out to be artificial, if even one stellar system shows definitive evidence of engineering, that single confirmation answers the question of whether we're alone, proves that technological civilizations exist and that they achieve capabilities far beyond what humanity has developed, demonstrates that the galaxy is populated and that we're joining context that's been operating without us for longer than we've existed, and that discovery, that recognition of our cosmic context, would be more significant than anything else astronomy has revealed about the universe. The stars are moving at impossible speeds, are travelling at velocities that natural processes struggle to explain, are distributed in patterns that don't match what ejection mechanisms predict, are showing properties that raise questions about whether everything we're observing is actually natural, and the artificial explanation, the hypothesis that some fraction represents deliberate relocations executed by civilizations with stellar engine technology, fits the observations at least as well as the strained natural explanations that keep being proposed and that keep failing to fully account for what we see. So maybe it's time to take the question seriously, to investigate whether stellar engines exist rather than assuming they don't, to search for signatures that would distinguish artificial from natural rather than defaulting to natural interpretation regardless of evidence. To recognize that the discovery of the century might be waiting in data we've already collected if we just bothered to analyze it properly with artificial hypotheses in mind. The velocities are real. The stars are moving. The galaxy might be more interesting than we've been assuming, and the only way to find out is to look honestly at what we're observing and to follow the evidence wherever it leads, rather than protecting comfortable assumptions about cosmic isolation that might be completely wrong. The velocity distribution of the hypervelocity star population creates additional puzzles that strengthen the case for investigating artificial explanations more seriously. Because if you examine the speeds at which these objects are travelling, if you plot the distribution and compare it to what natural ejection mechanisms predict, you find discrepancies that are difficult to reconcile through conventional astrophysics. The distribution should be smooth, should show gradual decline from lower velocities to higher velocities, with the higher speeds being rarest because they require the most extreme conditions to produce, should follow statistical patterns that gravitational slingshot mechanisms generate based on the distribution of encounter geometries and binary separations and black hole masses. But the observed distribution shows structure, shows clustering at specific velocity ranges that doesn't match the smooth predictions, shows gaps where fewer stars exist than models predict, shows excess population at velocities that should be rare if natural processes are solely responsible. And each of these features, each deviation from expected smooth distribution, requires explanation, requires either modifying natural models to account for the structure, which introduces additional parameters and complexity, or considering that some fraction of the population has velocities that were deliberately chosen rather than being random outcomes of chaotic gravitational interactions. The velocity clustering around specific values is particularly suggestive, because if civilizations are relocating stellar systems, and if they're optimizing for specific goals, they would converge on certain velocities that achieve those goals efficiently. If the objective is to reach the galactic halo, there's optimal velocity that minimizes transit time while avoiding excess energy expenditure. If the objective is intergalactic escape, there's minimum velocity required to overcome galactic gravitational binding. If the objective is to reach specific destination region, the required velocity depends on distance and desired transit time, so you might expect to see clustering where multiple relocated systems are traveling at similar speeds because they're pursuing similar objectives, where the velocities aren't randomly distributed across the full range of what's physically possible, but are concentrated at values that make strategic sense for common relocation goals. And if you see this clustering in observations, if the velocity distribution shows peaks at specific values, rather than being smoothly declining, that's signature that's more consistent with deliberate selection than with random natural processes. The directional distribution provides complementary information, because velocity is vector quantity, has both magnitude and direction. And while we've been discussing the speeds, the magnitudes, the directions matter too for determining what's producing these objects. Natural ejection from galactic center should produce roughly isotropic distribution where stars are flung in all directions equally. Natural ejection from supernova events should show some concentration towards spiral arms, where massive stars that produce supernova are most common, but should still show broad directional spread. But if stellar relocations are driven by strategic objectives, if civilizations are choosing destinations deliberately rather than accepting whatever direction ejection mechanism happens to provide, then directional distribution should show structure, should show concentration toward regions that are desirable destinations and avoidance of regions that aren't. Should show patterns that correlate with galactic structure in ways that reflect preferences about where to relocate, rather than just reflecting where ejection mechanisms are operating. Analyzing this requires careful accounting for observational biases. We're observing from specific location in the galaxy, can more easily detect stars moving in certain directions than others, can see different parts of the galaxy with different clarity. All of these selection effects influence what we observe and need to be corrected for before interpreting directional distributions as revealing underlying patterns, rather than just reflecting where we happen to be looking and what we can detect from our vantage point. But even accounting for biases, preliminary analyses suggest that hypervelocity star directions aren't purely random. Show some structure. Show correlations with galactic features that might indicate destinations are being chosen rather than being random. Show hints of organization that natural isotropic ejection wouldn't produce. Are suggestive rather than definitive, but are exactly the kind of evidence that should motivate more detailed investigation rather than being dismissed because artificial hypothesis is uncomfortable. The metallicity distribution of hypervelocity stars provides another test of whether the population is purely natural or includes artificial component. Because stellar metallicity, the abundance of elements heavier than hydrogen and helium, varies across the galaxy in predictable patterns. Stars near the galactic center tend to be metal-rich because that's where stellar formation has been most active and where successive generations of stars have enriched the gas with products of nucleosynthesis. Stars in the halo tend to be metal-poor because they formed early in galactic history before significant enrichment had occurred. And if hypervelocity stars are being ejected from galactic center through Hill's mechanism, their metallicity distribution should match the metallicity distribution of stars in the central region. Should be relatively metal-rich compared to average galactic population. Should show the chemical signatures of formation in environment where many previous stellar generations had enriched the gas. If they're being ejected from various locations through different mechanisms, their metallicity distribution should be broader, but should still match the average galactic metallicity distribution, weighted by where ejection mechanisms are operating. But if significant fraction represents artificial relocations, if civilizations are choosing which stellar systems to move based on criteria that include resource considerations, then metallicity distribution might be skewed. Might show preference for metal-rich stars because those are systems most likely to have rocky planets and abundant heavy elements. Might show avoidance of extremely metal-poor stars because those are less likely to have developed technological civilizations or to be desirable relocation targets. Might show structure that reflects selection criteria rather than just reflecting where natural ejection mechanisms happen to operate. Testing this requires spectroscopic observations that can determine metallicities for large sample of hypervelocity stars. Requires comparing observed distribution to predictions from natural models and from artificial selection models. Requires statistical analysis determining whether differences are significant or whether they could arise from observational biases or from natural variation in how ejection mechanisms sample stellar populations. All technically feasible but requiring dedicated observational effort and willingness to seriously evaluate artificial hypothesis rather than assuming natural explanation must be correct. The age distribution provides yet another discriminator. Young stars, objects that formed recently in cosmic terms within past few 100 million years, should be rare among hypervelocity population if ejection mechanism is Hill's process at galactic center. Because young stars haven't had time to migrate from their formation sites in spiral arms to central region where supermassive black hole can interact with them. The population should be dominated by older stars that have completed multiple galactic orbits and that have had opportunity to pass near enough to galactic center for ejection to occur. But if stellar relocations are common, if civilizations preferentially move younger systems because those have longer remaining lifetimes and represent better long-term investments, then age distribution might show different pattern, might include higher fraction of young stars than natural ejection would produce. Might show excess of systems in age ranges where technological civilization is most likely to have developed and where decision to relocate makes strategic sense from longevity perspective. Determining stellar ages is challenging, requires detailed spectroscopic analysis and comparison to stellar evolution models, introduces uncertainties that make statistical comparisons less definitive than they would be for properties like velocity or metallicity that can be measured more directly. But approximate age estimates are possible for many stars, and building distribution from available data could reveal whether young stars are overrepresented in hypervelocity population in ways that natural models struggle to explain. The companion star problem in binary systems provides perhaps the strongest single piece of evidence challenging natural ejection explanation while supporting artificial relocation, because Hill's mechanism works by tearing binaries apart, operates specifically on binary systems rather than on isolated single stars. The tidal forces that accelerate one star to escape velocity should simultaneously disrupt the binary bond, should leave both stars travelling independently with one ejected at high velocity, while the other remains captured or continues on modified orbit near the supermassive black hole. So if Hill's mechanism dominates hypervelocity star production, essentially all hypervelocity objects should be single stars, should be former members of binaries that have been separated from their companions through the ejection event. Finding hypervelocity binary, finding two stars still gravitationally bound while travelling together at speed sufficient to escape the galaxy, should be impossible, or at least extraordinarily rare, requiring very specific and unlikely conditions during the encounter that somehow preserve the binary bond despite tidal forces that normally tear such systems apart. Yet we've found at least one hypervelocity star with planetary companion as mentioned earlier, and searches for stellar companions for binary systems among the hypervelocity population are revealing that multiple examples might exist, are finding candidates that show characteristics suggesting they're binary systems despite travelling at velocities that natural ejection should not be able to impart while maintaining binary integrity. Are discovering that the population might include fraction of bound systems that shouldn't exist if natural mechanisms are solely responsible. And this is exactly what artificial relocation predicts. If you're using stellar engine technology that applies gradual acceleration over millions of years, rather than impulsive velocity kick from tidal encounter, binary systems can survive. The acceleration is gentle enough that gravitational binding between the stars can adjust gradually rather than being torn apart by sudden force. The orbital parameters evolve as the system accelerates, but the binary remains bound. Both stars move together to new location with their mutual orbit preserved, even though the entire system is travelling at hypervelocity relative to galactic rest frame. So finding hypervelocity binaries is strong evidence against natural ejection being dominant mechanism, and strong evidence supporting artificial relocation being at least partial contributor to population, is exactly the kind of observation that should motivate serious investigation of artificial hypothesis, rather than being explained away through increasingly contrived natural scenarios that require special circumstances that become less probable the more you stack them. The energy budget for producing hypervelocity population creates interesting constraints from both natural and artificial perspectives, because accelerating stars to these velocities requires enormous energy input. And whether that energy comes from gravitational slingshots around supermassive black holes or from stellar engines operating over millions of years, the total energy budget for creating the observed population is calculable and provides tests of whether proposed mechanisms can actually account for what we observe. For natural mechanisms, the energy comes from gravitational potential. Binary star system falling towards supermassive black hole converts gravitational potential energy into kinetic energy. When the binary tears apart, that kinetic energy gets partitioned, with one star carrying off substantial fraction as escape velocity, while the other star loses energy and remains bound. The process is efficient in the sense that no external energy source beyond gravity is required. But it's limited by how much gravitational potential energy is available, and by the rate at which binaries encounter the black hole in configurations that produce ejection rather than just orbital modification or capture of both stars. Calculate the rate at which such encounters should occur based on stellar density near galactic center, and based on fraction of stars that are in binaries, and based on orbital dynamics that determine what encounter geometries produce ejection. Multiply that rate by the average energy imparted per ejection to get total energy being channeled into hypervelocity star production per unit time, and compare that to what's required to account for observed population. The calculation suggests that galactic center ejection can produce the observed number of hypervelocity stars if mechanism operates for full galactic history. but it struggles to account for population if most hypervelocity stars don't actually originate from galactic center, as observations indicate. Requires either that ejection rate is much higher than expected, or that stars are being produced through alternative mechanisms that we haven't properly characterized. Creates tension between what energy budget allows and what population statistics suggest is actually happening. For artificial mechanisms, energy comes from stellar output. The star generates energy through fusion. Stellar engine captures fraction of that output and uses it to produce thrust. Over millions of years of operation, substantial fraction of stellar energy budget gets converted to kinetic energy of the system, and while individual systems' relocation requires enormous absolute energy, its small fraction of total stellar output over the operational period, the star continues shining, continues generating far more energy than the thruster consumes, is barely affected in terms of its evolution or lifetime by the mass loss that propulsion requires. Extrapolating to galactic population, if even small fraction of stellar systems are being relocated, if even 1% of stars have stellar engines operating at any given time, the total energy being channeled into artificial relocations could be substantial, could account for significant fraction of observed hypervelocity population, without requiring that natural mechanisms produce all examples. Could make the population comprehensible as mixture of natural ejections plus artificial relocations rather than requiring that exotic natural processes account for every observation. The technological evolution pathway that leads to stellar engine capability provides context for estimating how common such technology might be. Because building stellar engine isn't first step on technological development ladder, requires achieving multiple prerequisites, requires space access and orbital infrastructure, requires large-scale construction capability, requires materials science for structures that can survive near stellar environments, requires computational capability for managing complex systems, requires institutional continuity for projects that span millions of years. Humanity is nowhere near these capabilities currently. We can barely maintain presence in low Earth orbit, can barely build structures spanning few hundred meters, can barely plan projects lasting decades, let alone millennia or mega-years, are separated from stellar engine capability by gulf that might require thousands or millions of years of continued technological development to cross, assuming we survive and continue advancing rather than stagnating or regressing or destroying ourselves. But if technological development continues, if civilizations generally progress from planetary bound to spacefaring to stellar engineering capabilities given sufficient time, then the fraction of galactic civilizations that have reached stellar engine level depends on how long civilizations typically survive and develop before encountering barriers that prevent further advancement. If development time from radio technology to stellar engines is typically millions of years, and if civilizations typically survive for billions of years once they achieve stability, then a large fraction of existing civilizations would have stellar engine capability at any given time. And if stellar engineering is common among advanced civilizations, if it's standard rather than exotic technology, then expecting to see evidence of it in astronomical observations becomes reasonable, becomes prediction that we should test rather than assumption we should dismiss, becomes hypothesis that deserves investigation rather than speculation that serious researchers shouldn't discuss. The galactic coordination question raises fascinating possibilities about how artificial stellar relocations might be organized if they're occurring at significant scale. Because if many civilizations are moving stars, if stellar traffic is substantial, then coordination becomes important to avoid collisions and to optimize overall galactic organization. Individual civilization acting alone might choose relocation paths based purely on local considerations. But if multiple civilizations are active, cooperation might emerge to ensure that relocations don't interfere with each other and to manage shared galactic environment responsibly. Such coordination could produce structure in stellar distributions that reflects agreed-upon patterns rather than just reflecting individual decisions. Could create zones that are designated for specific purposes, regions that are preserved as nature reserves where natural stellar dynamics remain undisturbed, corridors that are designated as safe relocation paths where high-velocity transit is acceptable and where encounters are minimized through traffic management. Could organize the galaxy in ways that balance individual civilization needs against collective benefits from coordination. Detecting such organization requires looking for patterns at galactic scales, requires statistical analysis revealing structure that's too regular to be natural, requires identifying boundaries or gradients in stellar properties that correlate with organizational frameworks rather than with natural dynamical processes. All extremely challenging given limited data and given multiple selection effects that influence what we observe, but potentially achievable as datasets improve and as analysis methods become more sophisticated. The ethics of stellar relocation creates interesting questions that civilization considering such projects would need to address. Because moving a star affects everything in that stellar system, affects planets and any life that might exist on those planets, changes the environment in ways that might be beneficial or harmful, depending on perspective and depending on what timescales matter, raises questions about whether civilization has right to make such modifications unilaterally or whether consent is required from other affected parties. If the stellar system is uninhabited, if technological civilization has developed there but hasn't spread beyond their home planet, decision to relocate might be straightforward. Benefits accrue to that civilization directly. Costs are borne by them. No one else is affected in ways that require their input. The civilization can choose relocation if it serves their interests, and can decide against it if costs exceed benefits from their perspective. But if the system contains multiple inhabited planets, or if it contains primitive life that hasn't yet developed technology, decision becomes more complex. Does existence of non-technological life create obligations to preserve natural conditions? Does relocating stellar system constitute violation of rights of species that haven't consented to having their environment modified? Or does technological civilization's ability to accomplish relocation give them authority to make decisions affecting the entire system? Different ethical frameworks might reach different conclusions, might prioritize technological species' autonomy to modify their environment, versus might prioritize preservation of natural conditions for all life, regardless of technological status. Might focus on long-term benefits that relocation provides versus might focus on right of existing species to develop in their original environment without external interference, might develop norms that technological communities accept, versus might see conflict between civilizations with different ethical principles. And if stellar relocations are common, if ethical questions about how to manage shared galactic environment have been confronted by many civilizations, then solutions might have emerged, might have coordination mechanisms or agreed principles, or enforcement systems that manage how relocations proceed, and that ensure collective interests are considered alongside individual civilization preferences. Might have evolved galactic governance structures that operate on timescales we can barely comprehend, but that shape how stellar engineering is actually practiced. The observational signatures of stellar engine control systems provide perhaps the most definitive test of artificial hypothesis, because control systems would produce emissions and effects that natural stellar processes shouldn't create. Stellar engines need sensors monitoring thrust and trajectory. Need computers processing enormous amounts of data and calculating adjustments. Need communication systems coordinating between different components of the engine and potentially communicating with ground control on relocated planets. All of this infrastructure would consume power and would produce electromagnetic emissions that could potentially be detected if we searched at appropriate wavelengths and with appropriate sensitivity. The computational requirements are staggering but calculable. Managing stellar engine requires monitoring trillion kilogram per second mass flow, requires tracking position and velocity accurately enough to detect deviations from desired trajectory, requires calculating thrust adjustments and executing them through massive distributed systems. Requires doing all this continuously for millions of years without catastrophic failure. This is a computational challenge that dwarfs anything humanity has attempted, but that's feasible for civilization with computational technology beyond our current capabilities, and computation produces heat, requires energy input that gets converted to information processing, and that ultimately gets radiated as waste heat. The total power consumption might be modest compared to stellar output, but could still be substantial in absolute terms. Megawatts or gigawatts of computational power generating equivalent thermal emissions that would appear as infrared excess if the waste heat radiators were visible from Earth. Detecting this requires careful thermal modeling to separate natural stellar emission from potential artificial components, and requires sensitivity to detect modest excess against the overwhelming natural thermal background. The communication systems create another potential signature, because if stellar engine is being controlled or monitored from planetary surfaces, if operators are receiving data about engine performance and are transmitting commands or adjustments, then radio or optical transmissions might be occurring. Might use frequencies and modulation schemes that differ from natural astrophysical emissions. Might show time variability that correlates with orbital periods of planets, or with operational cycles of the engine rather than with natural stellar activity. SETI searchers have been looking for such signals for decades, but have been focused primarily on detecting deliberate transmissions aimed at announcing presence, or at communicating across interstellar distances. Haven't been designed to detect operational communications between stellar engine and planetary control centers, because that use case wasn't considered. But the signals would exist if engines are operating, would be brighter and more continuous than speculative interstellar greeting messages, because they serve functional purpose for civilization that's using the technology rather than being optional attempt at contact with unknown others. Redirecting SETI efforts toward detecting these operational signals, designing search programs specifically targeting stars that show hypervelocity or other characteristics suggesting possible artificial activity could provide more productive approach than current strategy of surveying vast numbers of stars hoping to stumble across deliberate transmission. Changes the question from is anyone trying to talk to us to is anyone doing anything that produces detectable emissions as byproduct, and the latter might be far more common than the former if most civilizations aren't particularly interested in announcing their presence to unknown species, but are actively using stellar-scale technology for their own purposes. The timeline for confirming stellar engines depends on whether astronomical community decides to take the question seriously and commits resources to systematic investigation. With current observational capabilities and with focused program designed to test artificial hypotheses rigorously, answer could be available within a decade. High-precision astrometry tracking acceleration of candidate stars, thermal imaging searching for infrared excess, radio surveys searching for operational communications, spectroscopic monitoring looking for compositional or velocity anomalies, statistical analysis comparing population characteristics to natural and artificial predictions, all technically feasible now, all could be executed with existing or near-term instruments. The limiting factor isn't technology, is willingness to pursue the investigation, is overcoming cultural resistance to treating artificial explanations as legitimate scientific hypotheses deserving serious attention, is convincing funding agencies that searching for stellar engines is valuable use of telescope time and research effort, rather than being waste of resources on fringe speculation. But if the investigation never occurs, if the questions never get asked seriously because artificial hypothesis is dismissed reflexively, then we might never know whether hypervelocity stars are artificial. Might continue interpreting all observations through natural framework even when artificial explanation fits better. Might miss the discovery of the century because our biases prevented us from investigating properly. And that failure would be on us, would be consequence of choosing comfort over truth, would be exactly the kind of mistake that future generations would look back on with disbelief that we could be so blind to possibilities that evidence was suggesting. The stars are moving at impossible speeds. The population shows patterns that natural processes struggle to explain. The energy budgets and the distributions in the companion systems and all the accumulated observations create picture that's increasingly difficult to reconcile with purely natural framework. And the alternative explanation, that advanced civilizations with stellar engine technology are relocating their stellar systems for strategic purposes we can only partially understand, fits many observations that otherwise require exotic and contrived natural mechanisms. So maybe, just maybe, it's time to look seriously at what the universe is showing us rather than what we assume it must be showing. Time to investigate whether we're sharing galaxy with intelligences that operate on scales we're only beginning to comprehend. Time to test whether the impossible velocities are actually engineered relocations rather than natural ejections. Time to follow the evidence wherever it leads rather than protecting assumptions that might be completely wrong. Because if even one hypervelocity star is artificial, if even one stellar system shows definitive evidence of engineering, everything changes. Our cosmic isolation ends. Our understanding of what's possible expands dramatically. Our place in the galaxy shifts from pioneers to newcomers in context that's been populated and organized long before we develop technology. And that discovery is worth pursuing, is worth investigating seriously rather than dismissing because implications are uncomfortable. The universe might be more interesting than we've been assuming. The galaxy might be more populated than we've believed, and the only way to find out is to actually look with open minds and honest analysis, rather than filtering observations through biases that prevent us from seeing what's actually there.